Okay, welcome back everyone. Here we're going to continue our discussion of uh, energy and energy conservation. And when we left off, we'd introduced this idea that we had potential energies, which we could define as essentially the work done, or the opposite of the work done, minus the work done by what we called conservative forces. Forces like the law of gravity, forces like the elastic restoring force, forces. These are conservative forces, so springs and gravity, but not things that are like friction that dissipate energy. And we'll get to sort of an exact definition of a conservative force here in this lecture. But for these conservative forces, for things like springs and gravity, then we can define a potential energy, which is a unique function of the position of those of objects under the influence of those forces. And then we can say that if the only things acting on a system, if the only forces acting on a system are these conservative forces, then the total mechanical energy of that system will be conserved, by which we mean that the total mechanical energy is the sum of kinetic energy and potential energy, so that the initial kinetic energy and the final, or the initial total energy and the final total energy will be the same. In other words, that the sum of the initial kinetic energy and the initial potential energy will be the sum of the final kinetic energy and the final potential energy, and that at any point during that motion, we can just add up all of the sources of energy, and they should be the same as we had at the start. Another way of looking at this is that any changes in kinetic or potential energy must sum up to zero, so that any energy gained by kinetic energy, for instance, must be lost by potential energy, and so on. So let's do another example here. It says we have a system of two paint buckets connected by a lightweight rope extended over a pulley, and this system is released from rest with a 12 kilogram bucket 2 meters above the floor and a 4 kilogram bucket resting on the floor. It says use conservation of energy to find the speed at which the 12 kilogram bucket hits the floor. All right, so as usual, we'll begin by drawing ourselves a picture. Here's our bucket number one, and there is a pulley and rope system. The rope goes up the pulley, and bucket number two is down here on the floor. So there's our floor, and this is a 12 kilogram bucket, and this is a 4 kilogram bucket. And the 12 kilogram bucket is a distance of 2 meters above the floor. So first thing is we can apply some physical intuition. We go, obviously the 12 kilogram bucket, being the heavier one, is going to want to fall, and thus will pull the 4 kilogram bucket upward. The next thing we would want to do is define an interesting moment in time, and obviously the moment that we start here, that's one of the potentially interesting moments in time. It's a moment in which we can say something about the system. In this case, that the 12 kilogram bucket is 2 meters above the ground, the 4 kilogram bucket is sitting on the ground, and neither bucket is moving. A second moment of interest would be when the 12 kilogram bucket is just about to hit the ground but hasn't done so yet, and the 4 kilogram bucket then would be up here. Whoops, actually, it will be right here at the same height. This is the 4 kilogram bucket. It'll be at the same height that the 12 kilogram bucket had been. Here's our pulley. Here's our rope going around the pulley again. And now, at this moment, our 12 kilogram bucket will be moving down at some speed v, and our 4 kilogram bucket will be moving up at some speed v. Okay, so if this is our second moment in time, again, just before that second bucket hits the ground, then what we should be able to say is the only force acting here is gravity. Gravity is a conservative force, and therefore we will be conserving the energy. In other words, that the total mechanical energy at moment 1 is going to equal the total mechanical energy at moment 2. So let's go ahead and just evaluate the energy at moment 1. All right, so the total mechanical energy at moment 1, that's going to be the kinetic energy at moment 1 plus, in this case, the gravitational potential energy at moment 1. And the total mechanical energy at moment 2 will be the total kinetic energy at moment 2 plus the total gravitational potential energy at moment 2. Okay. Let's label these buckets A and B, A and B, because we're going to have to break up these kinetic energies for the system and these potential energies for the system into energies for A and B, the A and B parts of that system. So the kinetic energy at moment 1, well, we can say that's the kinetic energy of bucket A at moment 1 plus the kinetic energy at bucket B at moment 1. And the gravitational potential energy at moment 1, that's going to be the gravitational potential energy at moment 1 of bucket A, and the gravitational potential energy at moment 1 of bucket B. Okay, and so we have 4 terms, 2 kinetic energy terms, 2 potential energy terms, and we're going to have the same 4 terms on the other side, except that it'll be at moment 2. So the kinetic energy at moment 2 of bucket A plus the kinetic energy at moment 2 of bucket B plus the gravitational potential energy at moment 2 of bucket A and the gravitational potential energy at moment 2 of bucket B. Okay, so we've written down all of the possible terms. Not all of these terms will be actually present. So for instance, at moment 1, neither bucket is moving. Therefore, neither bucket has any kinetic energy, and we can just set the kinetic energy of bucket A and bucket B at moment 1 to 0. Okay. Also, if we define the 0 point for our gravitational potential energy to be when a bucket is on the ground, then at this point here, moment 1, bucket B has no gravitational potential energy either because it is on the ground. And so that would be 0. And the only thing we're going to be left with is the gravitational potential energy of bucket A. So the gravitational potential energy of bucket A, that's mass of bucket A times 9.8 meters per second squared times the altitude of bucket A at moment 1. So that's the position of bucket A at moment 1, which in this case will be 2 meters above the ground. On the right-hand side, the kinetic energy of bucket A at moment 1, well, that's going to be 1/2 the mass of bucket A, or sorry, moment 2, 1/2 the mass of bucket A times the speed squared at which bucket A is moving, so v squared. And indeed, this v is what we're looking for. At that same moment, the kinetic energy of bucket B will be 1/2 the mass of bucket B times that same speed squared. They are moving in opposite directions. Bucket A is moving downwards and bucket B is moving upwards. But the kinetic energy only depends on the speed, not on the direction, not on the velocity. So the speed squared will be the same for both of these. The gravitational potential energy of bucket A, well, bucket A is on the ground, so the gravitational potential energy of bucket A will be 0, and the gravitational potential energy of bucket B will be mass of bucket B times 9.8 meters per second times the altitude of bucket B at moment 2, which again is that same 2 meters. So now we have an equation that on the left-hand side relates the gravitational potential energy of bucket 1, 2 meters above the ground, to the kinetic energy of both bucket A and bucket B moving at the same speed v, and the gravitational potential energy of bucket B now sitting 2 meters above the ground. So we're solving for v. Let's move the gravitational potential energy terms to one side and the kinetic energy terms to the other side. So mass of bucket A times g times y a 1 minus the mass of bucket B times g times y b2 is equal to 1/2 ma plus mb times v squared. We can note that ya1, that's a y, not a g, ya1 is equal to yb2 in this case. We're just going to call that y, and that'll allow us to simplify the left-hand side here as ma minus mb times gravity 9.8 meters per second squared times our height y is equal to 1/2 ma plus mb v squared. And we can just hide that for the moment. So now we're going to continue solving this equation for the for the speed here. So let's just rewrite this equation. Now I'm going to flip the sides here. 1/2 mass A plus mass B v squared, that's this side, is equal to mass A minus mass B times gravity times height. Pull the 2 over and pull the ma plus mb over, so v squared is equal to twice ma minus mb times g times y over ma plus mb. And so in other words, our speed will be the square root of that, 2 ma minus mb times gravity times height divided by ma plus mb, the square root of that. And so now we can start plugging in our numbers. Again, this is the square root of, at the top, 2 MA is 12 kilograms. 12 kilograms minus MB, 4 kilograms, times 9.8 meters per second squared, times our height of 2 meters, divided by MA plus MB, which was, our MA is 12 kilograms plus A 4 kilograms on the bottom. So this is the square root of 2. 12 minus 4 is 8 kilograms times 9.8 meters per second squared times 2 meters. And on the bottom, 12 plus 4 will be 16 kilograms. And indeed, we can see that 2 times 8 is 16, and that's going to cancel with the 16 on the bottom. So we're just going to be left with the square root of 9.8 meters per second squared times 2 meters. And now we get a calculator. And turn it on. It says 9.8 times 2. Take the square root of that. Our speed just before we hit the ground is 4.4 meters per second. So again, the strategy we use to solve this problem, draw ourselves a picture, identify a couple of interesting moments in time. In this case, the moment our experiment begins and the moment our experiment ends, just before the heavier bucket hits the ground. We then write down the energy at those two moments, and because we only have conservative forces here, because we only have gravity, then the energy at moment 1 is the energy at moment 2. And so now it's a matter of bookkeeping. We write down what are all the possible terms that energy could have at moment 1, what are all the possible terms that energy could have at moment 2, any of those energies that aren't occupied. So again, we're not moving at moment 1, so there's no kinetic energy terms. And bucket B is sitting on the ground, so it's not at altitude, so there's no potential energy term. So that got rid of 3 of the 4 terms on the left-hand side of this equation. Both bucket A and bucket B are moving at moment 2, and so we have to keep those kinetic energy terms. But bucket A is sitting on the ground, and therefore it has no gravitational potential energy, and we only have the 1 gravitational potential energy term. So we started with 8 terms, but it turns out that 3 of the 4 terms at moment 1 and 1 of the 4 terms at moment 2, those are all 0, so we can set them or take them out of the equation to begin with. And then we just write down the generic form for gravitational potential energy as it pertains to this particular moment. We write down the general form for kinetic energy as it pertains to this particular moment. We write down the form of gravitational potential energy as it pertains to this particular moment. And then we have our algebraic equation that we can solve for our unknown. And this is a pretty standard strategy for how to solve problems where the only forces at work will be conservative or energy conserving problems. We just write down the energy at moment 1, we write down the energy at moment 2, or we take a before and after or a point 1, point 2 approach, write down the energy at both times, and then it's just a matter of sort of bookkeeping. It becomes an accounting problem more than it becomes a sort of vectory things in motion kind of problem. Okay. So let's go back to our PowerPoint. Now, we haven't derived this conservation of energy in any case yet. I've just sort of stated it, but we can derive it at least for certain conditions already just using the physics that we know. So for instance, in the context of free fall, where we have an object that we have dropped from some height and it's just falling under the influence of gravity. Well, we already said from the kinematic equations that, or from our study of 1D motion, that the change in the final velocity squared will be the initial velocity squared minus this 2g times delta y term. Right, so this was the third of our one-dimensional kinematic equations, in this case with a constant acceleration of minus g. We can multiply both halves of both sides of this equation by 1/2 m, and that gives us two versions of kinetic energy, a final kinetic energy on the left and an initial kinetic energy on the right, and then a third term there which indeed looks very much like the gravitational potential energy term that we saw earlier last time when we looked at the gravitational potential energy. And indeed, if we move the kinetic energy terms to the left and the potential energy terms to the right, then the stuff on the left becomes the change in kinetic energy. The stuff on the right becomes minus the change in the gravitational potential energy, which allows us to write this as the total sum of changes in kinetic energy plus changes in potential energy must be 0, or also equivalently, that any kinetic energy gained must be the same amount as potential energy lost, and any potential energy gained must be the opposite of any kinetic energy lost. So, in other words, this is a sort of proof that conservation of energy does in fact at least hold true for the case of a freely falling object. We can make a more general derivation of this concept of conservation of mechanical energy in the context of any one-dimensional motion. So from Newton's second law, we have that the sum of forces acting on an object must be m times its acceleration, and the acceleration is the first time derivative of velocity. And if we expand the derivative here via the chain rule, the first time derivative of velocity is the dx dt times dv dx. Dx dt is just our velocity, and that's times dv dx. And then we return to Newton's second law. And so that allows us to write this top equation, F equals ma, in terms of F equals m times v times dv dx. And we can do that separation of variables thing we did before, so we move all the velocity-dependent terms to the right and all the position-dependent terms to the left, and we integrate in between initial and final position and initial and final velocity. The integral on the right is relatively easy to solve. It's just a power law. It's basically the constant times x dx, so that gives us our 1/2 v final squared minus 1/2 v initial squared, or in other words, the change in kinetic energy on the right, and this term on the left is minus the change in the potential energy. And so again, the sum of the changes in the kinetic energy and the sum of the changes in potential energy must all add up to 0. And in other words, again, energy is conserved. So these are both two ways that we can see that this law of conservation of energy was kind of hiding in plain sight. We just couldn't see it from the form that Newton had written down his laws. But if we make this definition for kinetic energy and we make that definition for potential energy, then indeed we can rewrite Newton's laws of motion and the kinematic laws of motion and recover this concept of energy conservation. And indeed, this gives us a way to define what a conservative force is. It's any force where this integral of the force dotted along, the force dotted into the path along which you integrate, if that integral always gives you the same value as long as you go from the same initial position to the same final position, then your force will be conservative. If the integral doesn't depend on how you get from A to B, how you get from the initial position to the final position, then your force is a conservative force. So it doesn't matter if you climb a ladder straight up or take a wheelchair ramp up at an angle, the change in your gravitational potential energy between where you start and where you end will be the same. It won't take, or and this integral will be the same whether or not you go straight up along a ladder or up diagonally along a ramp. Your change in potential energy will be conserved. That integral will be the same for both cases, and you will have a conservative force. But if the integral depends on the path you take, then your force is not conservative. So for instance, the reason that friction is not a conservative force is because the friction force will clearly depend, or the amount of work done by friction will clearly depend on how long the path you're moving through is. If we have if we're looking down from above and you move an object in a straight line from A to B, but there's always some amount of friction going the other way, right? So you're moving in this direction, but there's some friction in the opposite direction, then there will be an amount of friction. So if this is constant, then the work done by friction will just be minus F times that length from A to B, right? So in other words, the total amount of work done by friction will just depend on how long the path is. Well, if you go straight, that's one thing, but we could also go between those same 2 points on a long circuitous path with lots of curlicues, and clearly this path length over here is going to be longer than that path length over there, and so the work done by friction will have a larger absolute value than the work done by friction over here. You're going to lose more energy to friction by taking the scenic route than you would have by taking the direct route. So friction is not a conservative force. Right? Friction isn't a conservative force here, so we can't treat it as if we would like gravity or springs. Here's another example of a non-conservative force. The Coyote here has roller skates, and the roller skates have rockets on them. And if we imagine the Coyote has attached himself with a rope tied to a stake in the ground and is going around in a great big circle, right? Then we could ask ourselves, how much work do the rocket skates do on the Coyote as he goes around in a circle and comes back to his same location? So there's a forward force being applied to the Coyote, and that's going a tangential force. Meanwhile, he's going around in a circle. Well, the amount of work done by the rocket skates will just be F times dr. Well, he's always going to have an acceleration in the direction of his motion, so that's always going to be a positive amount of work, and it's just the total amount of work will just be the path length times his force here. And obviously that's not zero, so the work done can't just depend on his position. If this was a conservative force, then when he looped back around, the total work must be zero. Since in this case the total work isn't zero, then again, rocket skates aren't a conservative force. The application of rockets will always be adding energy to the system. The application of friction will always be subtracting energy from the system. Whereas, for instance, a spring will be adding energy to the system if it's relaxing, but it would also take energy away from the system as it's compressing. And so there is a chance that the elastic potential energy, or the elastic force can be conservative. Similarly, if you're moving up in a gravitational force, then gravity is pulling energy out of your system. And if you're moving down in a gravitational force, then gravity is adding energy to a system. So if you went around and in a loop under the influence of gravity, then also you will have no energy added or subtracted from your system. So any system where you can arrive back at your starting point and the total work done is zero, that's a conservative force. And any system where you arrive back at your starting point, like the Coyote on his rocket skates, and the amount of work is not zero, then that's a non-conservative force. Things like friction and rockets tend to be non-conservative forces. Things like gravity and springs tend to be purely conservative forces. And in the context of this, then we can generalize this idea of the work-energy theorem and say that the total work done by non-conservative forces will be the change in the energy of our system, will be the sum of the change of kinetic energies and potential energies. So now we have a way of dealing with both conservative forces and non-conservative forces from an energy perspective. If the only forces acting on our system are conservative, then we say energy is conserved and E1 equals E2. If there is a non-conservative force acting on our system, then what we say is that the change of energy, E final minus E initial, will be the work done by the non-conservative forces in the system. And the conservative forces in the system will just be showing up as part of the change in potential energy and the change in kinetic energy. Now, from the point of view of sort of a theoretical physics standpoint, even non-conservative forces are technically conserving energy, but they're putting the energy into a place where it's hard to get it back out again. And so the mechanical energy is being lost into other places where we can't get it back out again. So where does that energy go? It could go into the internal energy of the system. So if we, for instance, smash two cars together, then in that collision you will be bending the metal in the cars, and that bending of the metal in the cars changes the energy of the cars, that you're losing some energy into crushing cars like tin cans. And that's where some of the energy goes. If you, for instance, rub your hands together, all Mr. Miyagi style, then you can feel that the work you're doing, moving your hands against one another, is turning into heat or thermal energy in your hands. If you're burning rocket fuel, then or you're driving your car, then you're turning chemical energy into mechanical motion. You're adding energy into your system, and you're doing so by changing the chemical configuration of the fuel that you put into these systems. If you're powering a nuclear power plant, then you're using changes in the nuclear arrangement of the nucleuses of the atoms. That changes the energy of the atoms, and that comes out as heat, which you're using to run your power plant, and so on. There's always some place that this energy is coming from or that this energy is going to, but a lot of these things are not places that are easy to get it back out of. And so if we're just talking about mechanical motion, then we would consider these not conserved in the sense of the mechanical motion of our system, because the energy is either coming from a place that isn't a mechanical motion, or is going into a form which isn't accessible from a mechanical point of view. So this generalized conservation law, generally in physics we say that energy can't be created or destroyed, but from the point of view of mechanics, you can put energy into a form where you can't get it back out again, or you can take energy from a form which is not mechanical, turn it into mechanical energy. And in both cases, we would say the mechanical energy isn't conserved, and that the work done by that non-conservative process will change the total mechanical energy of our system. All right, so let's see if we can put this concept into some practice with a system where we're not going to be conserving all of the energy, where we're mixing some conservative forces with some non-conservative forces. Okay, so it says a 1,500 kilogram rocket is to be launched with an initial upward speed of 50 meters per second. In order to assist its engines, the engineers will start it from rest on a ramp that rises 53 degrees above the horizontal. At the bottom, the ramp turns upward and launches the rocket vertically. The engines provide a constant forward thrust of 2,000 newtons, and friction with the ramp is a constant 500 newtons. How far from the base of the ramp should the rocket start as measured along the surface of the ramp? All right, so let's draw ourselves a picture and see if we can understand what's going on. This is kind of a Jules Verne-esque version of launching a rocket, but we have a rocket that starts on a long ramp here. And there is some forward thrust down the ramp of 2,000 newtons and a constant amount of friction of 500 newtons going in the opposite direction. This ramp has a 53-degree angle above the horizontal, and then at the bottom of the ramp there's this sort of thing which turns whatever our down the ramp velocity is into a vertical velocity at the top. So from the standpoint of looking at the forces involved, the forces involved, we have a thrust force pushing the rocket down the ramp. Obviously, this is a non-conservative force. It's adding energy to our rocket. We have friction between the rocket and the ramp. That's obviously also a non-conservative force, in this case pulling energy out of our rocket. But we also have gravitation, right? There's a gravitational force. Gravity is a conservative force, and so we have some gravitational potential energy, and then we're looking at some kinetic energy. So there's three forces involved: thrust, friction, and gravity. One of those forces, gravity, is conservative. The other two forces are non-conservative. And so what we're going to say is the work done by the non-conservative forces in our system is going to equal the change in the energy of our system. It's going to be the final energy minus our initial mechanical energy. Okay, so the work done by non-conservative forces, let's evaluate that to begin with. All right, so the work done by non-conservative forces, well, that's going to be the work done by the thrust plus the work done by friction. Okay, the work done by thrust, well, that's going to be the thrust force, F sub t, times the distance, we'll call it L, the distance along the ramp, right? So the thrust is always in the direction of motion, so it's just F times L is our work, and the thrust therefore will be, or the total work will be F thrust times L. And the work done by friction will be minus the frictional force, in this case a kinetic friction force, the 500 newtons, times that same length. It's negative because it's pointing in the opposite direction of the motion. And so our net work, our work done by non-conservative forces, will be the thrust force minus the friction force times our length. Okay. The final energy of our system, well, that's going to be the final kinetic energy of our system, of our rocket, plus the final gravitational potential energy of our rocket. And if we define down here as gravitational potential energy equals 0, basically the ground is where, or the bottom of the ramp is where there's 0 gravitational potential energy, then the gravitational potential energy at the bottom of the ramp will be 0, and so the final kinetic energy will just be, the final total energy will just be the final kinetic energy, which will be 1/2 mv squared. All right. The initial kinetic energy of our rocket would be the initial kinetic energy, the initial energy of our rocket would be the initial kinetic energy of the rocket plus the initial gravitational potential energy of the rocket. If the rocket is starting from rest, then the initial kinetic energy will be 0, and the gravitational potential energy will be m times g times height, where the height here is how far our rocket is above the ground. So if we could go back to the work energy equation, which says that work by the non-conservative forces is the final energy minus the initial energy. And we replace all these terms with the expansions that we found here. So that's Ft minus Fk times our length L is equal to our final kinetic energy, 1/2 mv squared, our initial kinetic energy, mgh. And so now we have a statement, which is the work energy statement, that the work done by the non-conservative forces will be equal to the change in the energy of our system. And now we have to go back and figure out what it is that we know and what it is that we don't know. So we know the force of thrust is 2,000 newtons. We know that the friction force is 500 newtons. We know that the mass of our rocket here is 1,500 kilograms. And we know that the final velocity is 50 meters per second, or the final speed is 50 meters per second. We know g is 9.8 meters per second squared, so we know this, that, we know this and that, we know m and g. What we don't know is L and H. Indeed, L is what we're being asked to find, and H is related to L through a right triangle. That this is 53 degrees, that side is L and that side is H, so that opposite over hypotenuse, H over L, is the sine of 53 degrees. that h is equal to L times the sine of 53 degrees. And so we can replace our h here with L sine of 53 degrees. Like so. And rewrite our work energy equation that thrust minus friction times L is equal to 1/2 mv squared minus mg L sine of 53 degrees. All right, and now we know everything here except for L, and we can solve for L. So we'll collect the L terms over here on the left. Ft minus Fk times L plus mg L sine of 53 degrees is equal to 1/2 mv squared. So Ft minus Fk plus mg sine of 53 degrees times L is equal to 1/2 mv squared. We can divide both sides over this, move this thing, everything in the parentheses over. The length here that we need to start at is mv squared on the top. On the bottom we have 2 times force of thrust minus friction force plus mg sine of 53 degrees. And now we're ready to start plugging in some numbers. So L, our mass on the top is 1,500 kilograms. Our speed squared is going to be 50 meters per second squared. On the bottom we have 2,000 newtons minus 500 newtons plus 1,500 kilograms times 9.8 meters per second squared times the sine of 53 degrees. All right, so now let's start evaluating things. 50 squared on the top, that's 2,500, times 1,500 on the top, that gives us 3.75. 1, 2, 3, 4, 5, 6 times 10 to the 6 kilogram meters squared per second squared. And on the bottom we have 2 times, well, let's see, 1,500 times 9.8 times the sine of 53 degrees plus 1,500 newtons multiplied by 2 on the bottom. That gives us 2.6479, 2.6480 newtons. Times 3.75 and the answer is 142 meters is how long our ramp needs to be. Okay, well, let's try another example. Here it says Wile E. Coyote, who has a mass of 15 kilograms, is still scheming to catch that roadrunner. This time he wants to use a large compressed spring to launch himself down the road at 25 meters per second in order to overtake his would-be dinner. Assuming that he compresses the spring by 0.5 meters, what spring constant should he specify in his order to the Acme Spring Company? And when he eventually misses the roadrunner and lands on the road, how far will he slide before coming to a stop, assuming that a coefficient of kinetic friction of 0.8 between his fur and the road? All right. Well, let's take... Apologies, my mic came off. Let's take this a piece at a time. We're going to start here with just writing down some of the basic information. We have a mass of our moving object here of 15 kilograms. He wants to reach a speed of 25 meters per second, and the delta x for the compressed spring is half a meter, and the coefficient of friction is 0.8. All right, so let's take the problem a piece at a time. In the first part of the problem, he's trying to use a spring to propel himself down the road. So we have two interesting moments in time. The first one, we have a spring compressed by some distance delta x, where we have our Coyote. I'm not a cartoonist, so I'm just going to draw our Coyote as a box. And the Coyote isn't moving, so our initial velocity here is 0. And then at some later time, our spring has become uncompressed. The Coyote is flying through the air at a velocity v final of 25 meters per second. And so spring compression is a conservative force. So we can apply energy conservation here and say that the energy at moment 1 is equal to the energy at moment 2. At moment 1, that would be the kinetic energy at moment 1 plus the elastic or spring potential energy at moment 1. And at moment 2, we have the kinetic energy at moment 2, potentially the elastic energy at moment 2 as well. We could put gravitational potential energy here, but the Coyote isn't moving up or down, so whatever gravitational potential energy he has will just be a constant during this motion. So we'll just leave it off. And indeed, to begin with, he's not moving, so the potential energy at moment 1 is 0. And at moment 2, the spring is uncompressed, so the compression energy will be 0 at moment 2. And so we can write down the spring elastic potential energy here, 1/2 k times delta x squared. And on the right, we can write down the kinetic energy at moment 2, 1/2 mv squared. And this is now our algebraic equation that we can solve. In this case, we are looking for the spring constant k. We can cancel out the factors of 1/2, and pull the delta x squared over to the other side so that the spring constant k is the mass times final velocity squared over initial spring compression amount squared. And our mass is 15 kilograms. Our final velocity is 25 meters per second squared. Our compression here is 0.5 meters squared. So 25 divided by 0.5, square that, multiply by 15. And our spring constant here is 37,500 newtons per meter. That's how stiff the spring would need to be so that a half meter of spring compression gives the Coyote enough energy that it would reach 25 meters per second if all of that energy was converted into kinetic energy. For the second part of the problem, then now we have the Coyote has the kinetic energy he ended with at moment 2. So we go from moment 2, where the Coyote is moving at speed v, to moment 3, where the Coyote has come to a stop. The final velocity will be 0 meters per second. And in between this time, there has been a friction force, F sub k, acting through a distance d here. And in doing so, that friction force has been doing a negative amount of work on our Coyote. And so we can say that the work being done from moment 2 to moment 3, the work being done by friction in this case, that's our non-conservative force, is equal to the change in the energy. Okay, that's going to be equal to the kinetic energy at moment 3 minus the kinetic energy at moment 2. And the kinetic energy at moment 3, well, he's not moving at moment 3, so the kinetic energy at moment 3 is 0. Again, there's no gravitational potential energy coming in here, and there's no spring potential energy coming in here because there aren't any springs being compressed or released, and the Coyote's altitude isn't changing. So the only thing that's changing is the Coyote's kinetic energy. So the work done by friction will just be minus the kinetic energy the Coyote had at moment 2, so that's going to be minus 1/2 mv squared. And the work done by friction would be minus the friction force times the distance. Minus, because the friction will be in the opposite direction as the displacement. So the work done is negative, and that's going to be minus 1/2 mv squared. And to evaluate the strength of the friction, now we have to go back to our free body diagram on the Coyote. So there's a weight acting on the Coyote mg, there's a normal force acting on the Coyote n, and then there's a frictional force Fk here. The sum of vertical forces is going to be 0, and in this case that says that the normal force minus mg is 0, or that the magnitude of the normal force is just the weight of our Coyote. And the strength of the friction force is our friction coefficient times the magnitude of the normal force. So in this case, that's our friction coefficient times mg. And so we can plug that back in over to our work energy equation here and say that minus mu k times mg times d is equal to minus 1/2 mv squared. And now we finally have our algebraic equation, which we can solve for. In this case, we're trying to solve for the distance. The minus signs go away. We can pull the distance, or the mu k and mg over to the right here. So distance is mv squared over mu k mg. We can even cancel the masses. So that's v squared over mu k times g. And now we can plug in our numbers. V squared is 25 meters per second squared. Our mu k was 0.8, and g is 9.8 meters per second squared. And so 25 squared divided by 0.8 divided by 9.8 gives us a distance here of 79.7 or 80 meters is how far he would slide once the friction started to set in. All right, let's do one more example here. This one says a 60 kilogram skier with an initial speed of 13 meters per second coasts up a 2.5 meter high rise as shown in, or 2.5 meter high rise as shown in the figure. Her final speed at the top in meters per second find her final speed at the top in meters per second, given that the coefficient of friction between her skis and the snow is 0.8. All right, so let's go ahead and move that over here. So we again can draw our picture, choose our interesting moments in time. So our first moment here, there's our skier moving at some initial velocity, moment 1, or v1. This point at the bottom of the hill is probably a good place to define the gravitational potential energy to be 0. And then the second moment of interest would be up here, where our skier has a different velocity, v2, and is now up at some height h above where the skier started, where she started. And so, and then in here, what we know is that there is a coefficient of friction between those 2 points. We're going to go ahead and sort of treat this hill as a constant slope here, with an angle there of 35 degrees and a height here of 2.5 meters. And we're going to say on this slope the coefficient of friction is 0.08. So that as the skier goes up the hill here, whatever distance L is there, whatever the distance L is up that hill, there will be some work done by friction. There will be a change in altitude here done by, and therefore some change in the potential energy due to gravity. So because friction is involved, this is not a energy conservation problem, but a work energy problem. So again, we can say that the work done by non-conservative forces, in this case the work done by friction, will be the change in the total mechanical energy of the system. So that's going to be the energy at moment 2 minus the energy at moment 1. All right, so the work done by friction, well, there's a friction force. If we look at the free body diagram of our skier here, so there's our skier on the ski slope going upward. This skier has a force mg downward and a force, a normal force here, which is perpendicular to the slope, a normal force like so, and then a friction force which is perpendicular to the normal force. All right, well, we can say that the skier is not accelerating off of the hill, nor is the skier accelerating into the hill, so that the perpendicular components of force, the sum of the perpendicular components of force, must be 0. And so we need to convert the weight mg into horizontal and perpendicular components, right? So there is a, here's our angle, here's the weight force, and we have to convert this into a component perpendicular and a component parallel. So if this is mg, there's our 35-degree angle. So this is going to be mg cosine of 35 degrees. And this over here is going to be mg sine of 35 degrees. All right, so the sum of the perpendicular forces then, that's going to be the normal force minus mg cosine of 35 degrees. And that's got to be equal to 0. So in other words, the magnitude of the normal force is mg cosine of 35 degrees. Not just mg in this case, because she's going up the slope at an angle. And so the magnitude of the normal force is mg cosine of 35, which means that the magnitude of the friction force, F sub k, is our mu k times the normal force, which is mu k times mg cosine of 35 degrees. And so finally, the work done by friction is going to be minus F sub k times this distance L. And let's go ahead and relate that distance L to the height of the hill. So again, there's their 35-degree angle. There's our height. Here's our distance L. And h over L is opposite over adjacent. That's the sine of 35 degrees. And so L then would be h over the sine of 35 degrees. So that our work done by friction then is minus Fk times L, and Fk we said here is minus mu minus mu k times mg cosine of 35 degrees, and our L here is h over the sine of 35 degrees. So our work done by friction is going to be minus mu k times mg h times the cosine of 35 degrees divided by the sine of 35 degrees. Or in other words, this is minus mu kmgh divided by the tangent of 35 degrees. And that's the work done by friction. So that's the left-hand side of our work energy equation. The right-hand side of our work energy equation, well, the energy at moment 1, at moment 1 here we just have kinetic energy. So we have 1/2 mv1 squared, but we don't have any gravitational potential energy, and we don't have any spring potential energy. At moment 2, we're still moving, so we have some amount of kinetic energy, 1/2 mv2 squared. But now she's at a different altitude. She's moved up the hill, and so she has some gravitational potential energy plus mgh. And so the change in energy then, E2 minus E1, is going to be 1/2 mv2 squared plus mgh minus 1/2 mv1 squared. We can simplify that a little bit. So that's 1/2 mv2 squared minus v1 squared plus mgh is our delta E. And so now we can say that the work done by friction is the change in the kinetic energy. The work done by friction, we said, was minus mu k mgh over the tangent of 35 degrees. And the change in energy here is 1/2 mass times v2 squared minus v1 squared plus mgh. We have a mass term everywhere, so we can cancel the masses out. And what is it we're looking for? We want to know her final velocity at the top of the hill. We're looking to solve for v2. That. So we need to then move the other terms over here. So this is minus mu k over the tangent of 35 times gh over here equals 1/2 v2 squared minus v1 squared plus a gh term over here. So let's move this gh term over here. That gives us minus mu k tangent over tangent of 35 degrees minus 1, all of that times gh is equal to 1/2 v2 squared minus v1 squared. All right. And so let's continue this. So minus mu k plus, or mu k over tangent of 35 degrees plus 1 times gh. Let's go ahead and move the 2 over, so we'll put the 2 in there, equals v2 squared minus v1 squared. So v1 squared minus mu k over tangent of 35 degrees plus 1 times 2gh equals v2 squared. Let's go ahead and start plugging in some numbers here. So v1 squared, v1, well, we got to bring back the problem. I didn't write down what the initial velocity was. So our initial velocity here is 13 meters per second. So 13 meters per second squared minus our coefficient of friction here was 0.08 divided by the tangent of 35 degrees plus 1 times 2 times 9.8 meters per second squared times our height here, which is 2.5 meters. That's going to equal our V2 squared. So 0.08 divided by the tangent of 35 degrees plus 1. So that's 13 meters per second squared minus 1.11 times our 2 times 9.8 meters per second squared times 2.5 meters. So we multiply that by 2, multiply it by 9.8, multiply it by 2.5. So this is minus 54.6 meters squared per second squared, 13 meters per second squared. So 13 squared minus that equals V2 squared, and this is 114 meters squared per second squared is our V2 squared, and if we take the square root of that, our second velocity here is 10.7 meters per second, which is indeed slower than she started at, so that's a good sign. All right, so again, in this case, we had some non-conservative force. We had friction involved, so we had to use the work energy theorem that the change in work, or that the work done by friction was the change in the energy. We calculated the work done by friction. Here's where we have to do a bit of a Newton's law kind of problem to calculate the strength of the friction force. Then we use the definition of work to find the friction force. And then on the right-hand side, for the difference in energies, we just wrote down the terms of energy that were present at each place. At moment 1, we just had kinetic energy, whereas at moment 2, we had a combination of kinetic energy and gravitational potential energy. In this case, there were enough complications that the algebra got a little bit tricky, a little bit ugly. But in principle, again, it's just a matter of being systematic and writing down the various components of the energy, and then writing down the work and putting the various pieces together. All right, well, that's all for this time. We'll be back next time.